Well, good afternoon, good morning, or good evening, depending upon where you are in the world, and welcome to today's DevOps.com webinar. I'm Charlene O'Hanlon, moderator for today's event, and I welcome you. As always, we have a great webinar on tap, but before we get started, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the event, you will have the opportunity to access it later on demand. Following today's webinar, we will be sending out an email that contains a link to access the webinar on demand. And we are taking questions from the audience. So if at any time during today's presentation you have a question for our speaker, please don't wait, don't hesitate. Just use your GoToWebinar control panel and submit your questions. And we'll try to get to as many as we can before the end of today's webinar. Okay, with that, we will go ahead and kick off today's webinar, which is Cloud Native CI/CD, how engineering teams accelerate with Kubernetes, Docker, and Codefresh. Our speaker today is Apurva Ohm, who is Senior DevOps Associate at Bosch. Hi, Apurva, how are you?
Hey, I'm doing all right.
Good. Well, I know you have a great presentation ahead, so I'm going to put myself on mute and let you get right to it.
Perfect. Thank you so much. Hello again, guys. Thank you for that great introduction. My name is Apurva Ohm. I work as a Senior DevOps Associate for Robert Bosch. A little bit on my background. I began my career as a backend developer, coding in Java, picked up front-end and mobile app development along the way, becoming a full-stack developer. I have been designing and building different kinds of distributed and data-intensive systems for several years. It's a polyglot world now, so I'm constantly learning new languages, but I have coded in Java, Kotlin, and Node.js the most. I have worked across development and DevOps roles through my career. While working in development role, I've always been interested in how we are deploying our software, how are we configuring and building servers and infrastructure services. While working on DevOps and system administration side, I would think, how can I write code and script stuff to do building and maintenance of our infrastructure. Fortunately, with the way the industry is evolving, the two skill sets, namely development and DevOps, are starting to become complementary as opposed to separate roles. I work for Robert Bosch. We are an engineering and technology company with presence across 150 countries. Bosch's core operating areas are spread across 4 business sectors, namely mobility solutions. We make a lot of sensors that go into cars. Consumer goods, we make household appliances such as refrigerators, washing machines, etc. We also make power tools for construction industry. We also have presence in the industrial technology domain. We have SDKs on edge devices that are connected to large industrial machines and collect data around efficiency, maintenance, etc. We also make security cameras and heating products, thus giving us presence in the energy and building technology industry. Bosch is on the path to becoming a major player in the IoT space. Since Bosch services are so very ubiquitous, we have made a move to leverage our hardware presence to try and build a connected world. We plan to make all our electronic products web-enabled by the year 2022. Data generated by these connected devices is valuable and can be utilized to build additional products and services that add value to the industry. As a case study, I'm going to quickly show you one such product, which is Bosch Bluehound, catering to the connected construction industry. Bluehound is a cloud-based asset management and tracking platform. It is geared towards large to mid-sized construction companies. It takes traditional paper and pencil-based asset management and tool tracking to a cloud-based platform. How exactly Bluehound works? You basically buy subscription to Bluehound based on the number of assets or tools you want to track. You will be sent Bluetooth tags. You place these small tags on the tools or assets you want to keep track of. After that, Bluehound iOS and Android apps pick up the Bluetooth signal emitted by these tags and report the asset's current location. Change in location can also trigger events and generate user notifications. Once you're set up, you have access to your assets through the mobile apps as well as the web application on your phones or tablets. So let's quickly go through what we are going to cover today. I am going to share the experiential learning from having built a backend system composed of containerized microservices orchestrated by Kubernetes. Kubernetes itself is a very large topic to cover in a short span of 40 to 45 minutes. So I'm going to limit the scope of our presentation to 4 broader topics. First one, I'm going to talk about value proposition of Kubernetes, what it brings to the table and its own architecture. After that, I'm going to talk about certain Kubernetes features and how you can leverage them as good practices for a production-ready Kubernetes cluster. We are going to touch upon subjects of cluster isolation, scheduling, security, networking, and access and identity management. After that, we will cover drivers of high velocity engineering. I work with a relatively small team, and I will share with you the different components that have allowed us to achieve a high velocity and deliver feature releases very quickly. Thereafter, I will cover CI/CD with Codefresh. Codefresh is a Docker native CI/CD platform and is hosting today's webinar as well. We use Codefresh for all our development pipelines. Continuous integration and continuous delivery, when done for microservices, it becomes particularly challenging. With a monolith, you only have a limited number of CI/CD pipelines, but when the monolith is broken down into hundreds of microservices, the growth in CI/CD portion is explosive. Not only will you have hundreds of pipelines deploying to dev, staging, or production, but you will be making multiple releases in short periods of time and continually integrating your code. The cognitive overload to remember what goes where is impossible to deal with. Therefore, you have to automate your CI/CD with tools like Codefresh, Jenkins, etc. Time permitting, I will touch upon the various tools and open source applications which are very quickly proliferating in the Kubernetes ecosystem. So let's get started. What is Kubernetes? Kubernetes basically manages container-based applications and their associated networking and storage components. Kubernetes shifts the focus from underlying infrastructure components to the application workloads themselves. The application workloads become the star of the show as opposed to infrastructure. Benefits of using Kubernetes as an orchestrator, declarative approach to deployments, which means instead of deploying a service, you specify what you want to deploy and how many instances of it should be running. And Kubernetes deploys it for you and maintains the declared state of the service. For example, let's say you declare, keep 3 instances of Nginx running, and Kubernetes will do so. If an instance goes down for any reason, Kubernetes will spin up a new instance for you. The next benefit of using an orchestrator is it supports different types of workload. Kubernetes supports stateless as well as stateful applications. It also supports jobs and cron jobs. Kubernetes also ensures scalability, availability, and reliability. During the course of our presentation, we'll be able to learn how exactly it does that. Kubernetes also makes microservices-based applications easy to create and deploy. You can use any programming language, OS libraries to write your microservices, thus making it a polyglot platform. So there are great things that Kubernetes offers, but there were certain deciding factors that basically pushed us towards deciding to use Kubernetes. If you are considering, or your organization is considering moving in that direction, this might be a little helpful in terms of knowing what other people consider and use as parameters to decide whether they should go with a platform of this sort or not. So we chose Kubernetes because we wanted to be able to scale. It gives us the capability to scale out individual microservices based on customer usage and demand. It allows us to avoid downtime. We are able to use ingresses and canary deployments to basically make new feature releases without having to have any downtime at all. It has allowed us to reduce cost. We went from managing 50 virtual machines, which had our applications running, to roughly 15 or so. It of course allows for infrastructure abstraction. It shifts focus from the underlying infrastructure to the application workloads themselves. So a developer doesn't have to worry about which server they're going to deploy their service to. They just create a deployment object and give it to the Kubernetes infrastructure, and it deploys it for them. And last not but the least, greater developer velocity. So I'm going to touch upon this later on in the presentation, how it has enabled our team to achieve better velocity as compared to before. Let's quickly look at the architecture of Kubernetes itself, how it does the magic that it does, and the different components in there. So Kubernetes has two different components. The first is the master component, and the second is the node component. The master component provides the cluster's control plane. Master components make global decisions about the cluster, and they detect and respond to cluster events. The master realm is primarily made up of four components, subcomponents actually. First one is the Kube API server. The API server is how the underlying Kubernetes APIs are exposed. This component provides the interaction for management tools such as kubectl or the Kubernetes Dashboard itself. The second subcomponent is etcd. To maintain the state and configuration of your Kubernetes cluster, the highly available etcd key value store is used by Kubernetes. The next subcomponent is kube scheduler. When you create or scale applications, the scheduler determines what nodes can run the workload and starts them. Factors taken into account for scheduling decisions include individual and collective resource requirements, affinity and anti-affinity specifications, hardware, software, or policy constraints, etc., etc. Then the next subcomponent is Kube Controller Manager. The Controller Manager oversees a number of smaller controllers that perform actions such as replicating pods and handling node operations. Some examples of controllers are node controller or replication controller or endpoint controller. The next component is the node component in the Kubernetes architecture. This is where your actual application workloads run. The node components are orchestrated by the master components in essence. So there are basically three node components that are deployed to node VM when you spin it up. The first one is kubelet. Kubelet is the Kubernetes agent that processes the orchestration request from the cluster master and scheduling of running the requested containers. Virtual networking is handled by the kube proxy on each node. The proxy routes network traffic and manages IP addressing for services and pods. And last one is container runtime. It is the actual component that allows containerized applications to run and interact with additional resources such as virtual network and storage. Kubernetes supports several container runtimes. Docker is just one of them. It also supports Containerd or the RKT implementation of Kubernetes CRI, which is RKT-let. Actually, any container system can that basically implements the Kubernetes CRI, which is Container Runtime Interface, can work with a Kubernetes cluster. All right, excuse me. Now let's touch upon the topic of cluster isolation. Because your entire Kubernetes cluster is offered as one abstraction, and developers don't really decide which server their applications are going to be deployed on, there has to be some mechanisms built into the platform for the cluster operator to be able to give some flexibility to the developer to decide where the service might potentially be deployed. So the first topic that I'm going to touch upon is physical versus logical isolation. So a common approach to cluster isolation is to use physically separate physically separate clusters. In this isolation model, teams or workloads are assigned their own clusters. This approach often looks like the easiest way to isolate workloads or team, but it adds additional management and financial overhead. Physically separate clusters usually have a low pod density, as each team or workload has their own AKS cluster. The cluster is often over-provisioned with compute resource. Often a small number of pod is scheduled on those nodes, worker nodes. Then you could alternatively choose to do logical isolation. With logical isolation, a single cluster can be used for multiple workloads, teams, or environments. Kubernetes namespaces form the logical isolation boundary for workloads and resources. Logical separation of clusters usually provides a higher pod density than physically isolated clusters. There's less compute capacity that sits idle in the cluster, leading to better resource utilization. When combined with Kubernetes Cluster Autoscaler, you can scale the number of nodes up or down to meet your customer demands. So there's no rule of thumb. You basically need to use your judgment when trying to decide the number of clusters for your team or organization. Try to minimize the number of physical clusters you deploy by using logical isolation, but there are certain circumstances where you just can't avoid doing a separate physical cluster. What a lot of teams do is dev, QA, and staging environments sit in one cluster with logical isolation, and production environment has a physically isolated separate cluster. The next topic I'm going to talk about is resource quotas. The Kubernetes scheduler provides features that let you control the distribution of compute resources or limit the impact of maintenance events. Resource quotas and limits are placed in the pod specification. These limits are used by the Kubernetes scheduler at deployment time to find an available node in the cluster. These limits and requests work at the individual pod level to provide a way to reserve and limit resources across a development team or project, or even a set of applications. You should use resource quotas at namespace level for, let's say, compute resources, such as CPU and memory, or GPUs, or for storage resources, which can include specifying the total number of volumes or amount of disk space for a given storage class. Or you could even apply resource quota for object count, and you can specify the maximum number of secrets, services, or jobs that can be created in the particular namespace. This example YAML manifest sets a hard limit of total of 10 CPUs, 20 gigs of memory, and 10 pods. This resource quota is then applied to a namespace. That's what you see underneath when you see the kubectl command with the apply namespace in there. If a developer tries to deploy pods without defining resource requests and limits, as a cluster operator, you can either reject the deployment or you can configure default requests and limits for a namespace, which will be applied to the deployment automatically. One important thing to note is Kubernetes doesn't overcommit resources. Once the cumulative total of resource requests or limits passes the assigned quota, no further deployments are successful. So in order to be able to gauge how much resources are being currently consumed by the services running on your cluster, it's very important that you apply resource limits on your pod deployments. There's a tool available called KubeAdvisor. It is an open source tool which allows you to detect these issues in your cluster and find the pods that don't have resource requests and limits defined. You should regularly run KubeAdvisor on your cluster, especially if you don't assign resource quotas to your namespaces. You would want to see which pods don't have resources assigned to them, request and limit, and then this tool would tell you, and then you would go ahead and assign them the resources. Actually, I'm going to quickly run this command in the command line and show you what that does. Okay, maybe I changed the image name. Okay, never mind. All right, let's move on. Pod disruption budget. So to basically maintain the availability of applications, you should define pod disruption budgets to make sure that a minimum number of pods are available in the cluster. To mitigate involuntary disruptions, which could be hardware failure on the physical machine, or kernel panic, or the deletion of node VM, you will use multiple replicas of your pods in a deployment and run multiple nodes. To mitigate voluntary disruptions, such as cluster upgrades or an updated deployment template, Kubernetes provides pod disruption budgets that let the cluster operator define a minimum available or maximum available resource count. These pod disruption budgets let you plan for how deployments or replica sets respond when a voluntary disruption event occurs. Let's look at an example of a replica set with 5 pods that run Nginx. The pods in the replica set are assigned the label app is equal to Nginx front end. During a voluntary disruption event, such as a cluster upgrade, you want to make sure at least 3 pods continue to run. This YAML manifest for a pod disruption budget object defines these requirements. The second pod disruption budget object you see is basically used to define a maximum number of unavailable instances in a replica set. It defines that no more than 2 pods in the replica set should be unavailable. So it's the other way around. Next one is taints and tolerations, another feature that the scheduler offers. Let's say you want to limit access for resource-intensive applications, such as Ingress controllers, to specific nodes. The Kubernetes scheduler can use taints and tolerations to restrict what workloads can run on nodes. A taint is applied to a node that indicates only specific pods can be scheduled on them. Toleration is then applied to a pod that allows them to tolerate a node's taint. So Kubernetes only schedules pods on nodes where a toleration is aligned with the taint, if that makes sense. As an example, assume you have a node pool in your cluster for nodes with GPU support. You define names such as GPU, then a value for scheduling. If you set this value to no schedule, the Kubernetes scheduler can schedule pods on the node if the pod doesn't define the appropriate toleration. With a taint applied to nodes, you then define a toleration in the pod specification that allows scheduling on the nodes. This example defines the key SKU equal to value GPU and effect equal to no schedule to tolerate the taint applied to the node. When this pod is deployed, Kubernetes can successfully schedule the pod on the nodes with the taint applied. One thing to note is taints and tolerations are used to logically isolate resources with a hard cutoff, emphasis being on hard cutoff. If the pod doesn't tolerate a node's taint, it simply isn't going to be scheduled on the node. An alternate approach to the hard cutoff of taints and tolerations is to use a relatively softer node selector. Pods without a matching node selector can be scheduled on labeled nodes. This behavior allows unused resources on the nodes to consume, but gives priority to pods that define the matching node selector. So this kubectl label node k8 node pool 1 node hardware is equal to high SSD memory. You're basically labeling your node with this label. And then in the pod specification, you add the node selector property to define a node selector that matches the label set on a node, which is node hardware is equal to high SSD memory. That's what you see in the YAML manifest here on the screen. Next one is node affinity. A node selector is a basic way to assign pods to a given node. More flexibility is available using node affinity. With node affinity, you define what happens if the pod can't be matched with a node. So you can require, emphasis being on the word require, that Kubernetes scheduler matches a pod with the labeled host, or you can prefer, again, emphasis being on the word prefer, a match, but allow the pod to be scheduled on a different host if no match is available. This example here on the screen sets the node affinity to require during scheduling, ignore during execution. This affinity requires the Kubernetes scheduler to use a node with a matching label. If no node is available, the pod has to wait for scheduling to continue. If you wanted the pod to go ahead and schedule nevertheless, you would, instead of using require during scheduling, you would say prefer during scheduling. So the last trick in the scheduling magic box for Kubernetes is interpod affinity and anti-affinity. Let's just look at, understand this with the help of an example. Let's say you have a web application that also uses a cache like Redis. You can use pod anti-affinity rule to request that the Kubernetes scheduler distributes replicas across the nodes. You can then use affinity rules to make sure that each web app component is scheduled on the same host as the corresponding cache. And if you did that, then the distribution of pods across the nodes would end up looking like this, wherein each web app has access, very close proximity access to a cache because they're both sitting on the same node in the cluster. All right, now let's move on to the topic of security. You need to define pod security context to limit the actions that containers can perform. This is particularly important for node security. These pod security contexts are built into Kubernetes, and they let you define additional permissions, such as user or group to run as, or what Linux capabilities to expose. We know that we should grant users or groups the least number of privileges required. By same principle, containers should also be limited to only the actions and processes that they need. In this example, pod manifest, you see run as user is set to 1000, fs group is set to 2000. If these weren't specified, the container would give it the root access. Sorry, the container would get root access on the host operating system. Then you see the container has access to netadmin and systime Linux capabilities only. To minimize the risk of attack, you don't configure applications and containers that require escalated privileges or root access. In this example, you see allow privileged escalation is set to false in the pod manifest. That's exactly what it does. I have a pod running. Let's see if this works in my cluster. So you will see two pods running here in this Kubernetes cluster. One has no security context defined and the other has a security context defined. So I'm going to exec into the one that has a security context defined. So all right. So when I type, I want to see the ID. You see that whatever I had defined in my pod manifest, which was run as user 1000, fs group 2000, it's all in here. And your group ID is 3000. I think I missed out on placing the group ID, but this manifest has group ID set to 3000. So I come here, this is what you're seeing, run as user, run as group, and fs group, 1000, 3000, 2000 respectively. Now, if I say, let's say, I try to create a file with a little text in there. The container doesn't have permissions to create a file there, so it denies it. If it were running as root, then it would have been able to create that file. Now, another thing that we want to see is, so I have defined a volume in this pods manifest, and then I have mounted that volume at this location /data/demo. So I'm gonna cd into that location, cd data, and when I do ls, I'll see demo in there. So I go into demo, and now I'm gonna try. You saw it was denied permission to create a file at that location. However, because this mount path it belongs to the pod itself, it's the owner, it should be able to create a file here. So let's do that. So you see it was able to create the test file. Now I'm going to do a long listing, and you see that 2000, which was the fs group set here in the pod manifest for the container, that's the owner of this file, 2000. Now let's all right, perfect. That's about it. I'm going to exit out of here, go back to my presentation. All right, so for more granular control of container actions, you can also use the built-in Linux security features such as AppArmor or seccomp. These features are defined at the node level and then implemented through a pod manifest. Built-in Linux security features are only available on Linux nodes and pods, however. So AppArmor is one of those Linux kernel security modules. You basically, it is available as part of the underlying node operating system, and it allows you to limit the actions that containers can perform. It works for any application that runs on Linux, not just Kubernetes pods, since it's a Linux kernel security concept. You create AppArmor profiles that restrict actions such as read, write, or execute, or system functions such as mounting file systems. This feature is defined at node level and then implemented through a pod manifest annotation that you see here on the screen, container AppArmor security beta Kubernetes IO. And I will show you if this is. You can see that AppArmor is enabled in this sandbox cluster that I created. So a lot of implementations come with the Kubernetes implementations with different cloud providers come with AppArmor and SecComp enabled by default. All you would have to do is go in there and configure additional profiles on top of default. So SecComp is also another one of the Linux kernel security modules. It works at the process level. It is natively supported by the Docker runtime. With SecComp, the process calls that containers can perform are basically limited. You create filters that define what actions to allow or deny, and then use annotations within a pod YAML manifest, which you see here on the screen, seccomp.security.alpha.kubernetes.io, to associate with the SecComp filter, thus only granting the container the minimal permissions that are needed to run and no more. All right, so the last thing that I would like to share in terms of security with you, node security particularly, is a Kubernetes Reboot daemon tool. A lot of times when you apply security patches to the host operating system, it needs a reboot. Rebooting it immediately would be irresponsible and it would kill off instances of your service running on that particular node. So you need to reboot the instance, however, responsibly. You need to allow Kubernetes to cordon and drain off all the pods or deployments on that particular node, deploy them elsewhere, and then you would want to reboot that instance. So Kubernetes Reboot daemon is a Kubernetes daemon set that performs safe automatic node reboots when the need to do so is indicated by the package management system of the underlying operating system. It watches for the presence of a reboot sentinel at /var/run/reboot required. And it utilizes a lock in the API server to ensure only one node reboots at a time. Optionally, you can even configure it to defer reboots in the presence of active Prometheus alerts or selected pods. Now, I would like to talk about the umbrella good practices for ensuring strong cluster security. You want to restrict access to the API server as well as etcd. You want to use third-party authentication for API servers. API server doesn't come with any kind of security concepts associated with it, particularly the identity management concepts. So most of the cloud providers, both Google, AWS, as well as Azure, they're all, even OpenShift, they're all building integrations of AKS with their own identity management provider, which is OAuth or OpenID compliant. You want to enable audit logging. You want to rotate infrastructure credentials frequently. You want to encrypt secrets at rest in etcd, and you want to regularly upgrade Kubernetes cluster. Now let's quickly talk about the networking model. Kubernetes imposes the following fundamental requirements on any networking implementation. First one is IP per pod model. That is, you don't need to explicitly create links between pods, and you almost never need to deal with mapping container ports to host ports. This creates a clean, backwards compatible model where pods can be treated like VMs or physical hosts from the perspective of port allocation or naming or service discovery. The second requirement is agents on a node, such as system daemons or kubelet. It can communicate with all pods on that node. There are multiple implementation of the Kubernetes network model specification. Some of the examples are implementations from vendors such as Flannel, Cilium, Project Calico, WeaveNet, Azure CNI, etc. To distribute your HTTPS traffic to your applications, you want to use Ingress controllers. Ingress controllers provide additional features over a load balancer and can be managed as native Kubernetes resources. A load balancer can distribute customer traffic to applications, but it's limited in what it understands about the traffic. A load balancer resource basically works at layer 4 and distributes traffic based on protocols or ports. Applications should use Kubernetes Ingress resource because ingresses work at layer 7, and they can distribute traffic based on a URL of the application, as well as handle TLS or SSL termination and everything else that comes with a layer 7 load balancer. This ability also reduces the number of IP addresses you expose and map. With a load balancer, each application typically needs a public IP address assigned and mapped to the service in the cluster. With an Ingress resource, a single IP address can distribute traffic to multiple applications. Different vendors have implementation of Ingress controllers with their products. Nginx, Edge Proxy, Envoy, and Traffic are some of the examples. Next, you want to configure network policies in your cluster. A network policy is a specification of how groups of pods are allowed to communicate with each other and other network components. Network policy resources use labels to select pods and define rules which specify what traffic is allowed to the selected pods. You want to be careful when you select your CNI provider, because network policies are implemented by the network plugin. So you must be using a network solution which supports network policy. In this example that you see on the screen, incoming connections to pods with label color is equal to blue are allowed only if they come from a pod with color is equal to red on port 80. That's what this network policy on the screen is doing in the cluster. Next, let's talk about access and identity management. Use Kubernetes role-based access control to define the permissions that users or groups have to resources in the cluster. Create roles and bindings that assign the least amount of permissions required. This manifest shows how to define an all access role. This role can perform any action which corresponds to the verbs here. Create, delete, or read on all resources in all API groups. The second manifest shows how to bind the all access role to a user represented by janedoe@demo.com. So I hope you have taken away some useful information from all the topics that I covered. If either you're already running a Kubernetes cluster, then you can apply some of those good practices here, or if you're considering one, you now know what are the different feature sets that Kubernetes offers to you. Now, the next topic that I'm going to talk about is how Kubernetes has allowed my team to attain better speed compared to before. Kubernetes is popularly known for all these great capabilities, but I have come to champion Kubernetes for the high velocity engineering it enables. It has allowed our small teams to build infrastructure, create and deploy services for feature releases to customers, all in a short period of time. Let's see let's get into the hows of how Kubernetes enables speed. First one is containerization. Docker images are first-class citizens. All of our workflows are Docker native. Once you package an application into a Docker image, you don't have to care about dependencies, the underlying operating system, or the underlying infrastructure, as a matter of fact. Now let's talk about what are some of the advantages that I saw when I and my team started to use Docker containers. We packaged our applications in Docker containers and deployed them. So what were the advantages we saw over when we were not Dockerizing our containers and running applications natively on the host operating system? So if it ran in development, it will run in production. Images are immutable. So you could technically carry the same image from development to QA to staging to production. You want to closely couple your images to the code repository, and you can do that by tagging images with the commit SHA. Let me show you a little something here. Let's go to images. This is the Codefresh console, by the way. I'm going to come back to this console really in a short period of time. So this is how my image is tagged, and you can see this little number at the end. That's basically the shortened form of the commit SHA. So this would allow me to track back to my code commit, what exactly went into this release. And one great thing that Codefresh offers is you basically click on the commit and it takes you to your repository and the exact commit that you did for that particular release. All right, next, reproducing bugs is a lot easier. This is going back to the previous point. If you can move images between different environments, you can even debug images from production to your dev environment. Then easy rollbacks. If one of your current releases didn't work, you simply just deploy your previous image and roll back. We use Azure Container Registry to store all of our images. It acts as a private registry for us. Some good practices would be, I mean, you can run and manage your own container registry, but it's just easier if you're in the cloud and there's already a managed service available to do so. You need to update base images using ACR tasks. If you're using Azure's container registry, then they have something called ACR tasks, which allow you to update the base images automatically. I'm sure in other cloud providers, there are comparable concepts already there or being built. You also want to scan images for vulnerabilities using Twistlock or Aqua Security. The next driver in ensuring good speed for our team was using a managed Kubernetes cluster. I talked about all these great things Kubernetes does. However, building an entire cluster ops team, we did not have the bandwidth for that. So we were leaning more towards a managed container orchestrator like Azure Kubernetes Service. So irrespective of the cloud, managed Kubernetes services are available in all the major leading cloud providers. So benefits of using AKS as the orchestrator is basically a managed Kubernetes service reduces the complexity for cluster deployments and core management tasks, including coordinating upgrades. AKS does a lot of heavy lifting by managing the Kubernetes control plane, cluster security, as well as network plugins. The second reason you would want to go to a managed service is because all cloud providers, including Azure, are building easy integrations with other cloud resources, such as the Active Directory or the Key Vault or the Container Registry or the Traffic Manager or the Application Gateway on their respective clouds. So Azure Managed Cluster master nodes, you can see here in this picture, I talked about scheduler, API server, etcd, and controller manager, which form the master components of a Kubernetes cluster. They're all managed by Azure if you're in the Azure cloud, and respectively for the other clouds. And for the nodes, not just the master components, when you spin up a managed Kubernetes cluster, the node components, the 3 node components, kubelet, kubeproxy, and container runtime, are also provisioned and configured for you on the worker nodes. So all you have to do after that is start deploying your applications with minor cluster configuration. So again, AKS supports pod security context, Linux security modules such as AppArmor, SecComp, and SELinux. I already talked about the details of these great features. These come enabled in an AKS cluster by default. I am using Azure Kubernetes Service as my reference point when I talk about a managed service, because that's where we host our applications. But all of these great things I'm talking about are available in most of the cloud managed Kubernetes services. Again, AppArmor and SecComp, they're both available on AKS nodes. Networking in the AKS is basically done through an Azure Container Networking Interface, CNI. Every pod gets a unique IP address from the subnet and can be accessed directly. Azure provides 2 ways to implement network policy: Azure Network Policies and Calico Network Policies. I'm going to just point out one thing, that Azure is building a lot of native integrations with different Azure resources right now. So that when your pod can basically have an identity in the cluster, and you don't have to like give it credentials within the image itself, or you don't have to basically give credentials as secret in your cluster. The pod itself will be able to authenticate with Azure Active Directory, get an access token, and then be able to access other Azure resources. So in the interest of time, I'm going to skip a couple of slides here. Next driver is Helm charts. Helm charts have been very useful for us. You can basically deploy a lot of infrastructure services in different environments if you already have a configured and prepared Helm chart. Onboarding new engineers is quicker because all the complexity of deployment is abstracted away. You can spin up ephemeral or short-lived environments to test your application stack, and production releases are in general smoother. So let's get to CI/CD with Codefresh. I talked about these great things: Kubernetes, container native services, Helm charts. I think Codefresh, it kind of just ties in together all these great features, and in itself becomes like a driver of high velocity engineering for your team. So I'm gonna show you a couple of pipelines. Let's go here. All right, so I'm going to run this pipeline destroyer here so that I can delete all the pipelines. While it does that, let's go and look at the script for these pipelines. All right, so basically the pipeline destroyer is using a Codefresh CLI and then running these Codefresh delete pipeline commands to delete those particular pipelines. After this is done, I am going to go to the pipeline creator, which basically creates the pipeline for this project for me. I don't have to manually go in and create separate pipelines. So what this does is, let's say this is the root of the project here, this scheduled events portion. And what it does is basically it makes this Codefresh/spec folder, which is this folder here, the working directory. And then it has access to all these 4 YAMLs, which represent the different pipelines that I want to deploy. So it goes to this working directory. It says, find all YAMLs in this spec folder. And then for each of these YAMLs, run the command create a pipeline with these YAML as the manifests in there. So that's what the pipeline creator does. Now let's look at one of the specifications of the pipeline. Let's go to the dev one. What this does is basically clones my project, which is the scheduled events. It adds a trigger to my pipeline. So you want to automatically trigger builds and deployments when you push code to repositories. So this is a dev trigger. That means if you push code to the develop branch, it should trigger a deployment to your develop Kubernetes environment. So I want this pipeline to be triggered when somebody pushes code to the develop branch, or when somebody creates a pull request, let's say from a feature branch, and wants that pull request to be merged to a develop branch. So I want both of those events to create a trigger for this pipeline. And what this basically does is basically it sets the target branch, which is the develop branch. If you wanted, you could even do a comment regular expression in there to say, hey, if somebody types this ABC comment in there, git commit, trigger this branch, but I'm not doing that here. Then what this does is pull request target branch regex. This essentially says that when somebody creates a pull request from a feature to a develop branch, trigger only the develop branch. Why? Because feature branch has already been tested. You're merging code from feature branch to the develop branch. You want the develop branch pipeline to be triggered, and therefore consequently the new image deployed to the dev cluster. Then what I'm doing is I am basically going to use a spec template with some environment variables injected in there. These are my environment variables, which is the Helm chart reference itself, the namespace, and the name of my Kubernetes cluster in which I want this deployment to go to. So this cube context, basically the Codefresh platform understands this because I've already created an integration with my Kubernetes cluster. And this is just an alias that I'm using in my pipelines. Codefresh in the background does all the authentication and acquiring token and then deployment stuff for me because I've already done the integration. So that's what it does. Then it pulls up this template, this pipeline-dev.yaml in the pipeline folder, which is here. And then it deploys this pipeline. Now let's look at what the actual pipeline does. So there you can define different stages in there. First one, you clone the repository. This repo name is the name of your project, and branch is the target branch, which I injected from the spec. Then you get the tiller version. I am extracting the tiller version because Helm is undergoing a lot of development right now. And with every new release, I don't want to have to come back and change my pipelines to reflect the new client or server versions. So I'm just extracting it from my Kubernetes cluster. I can independently upgrade my cluster and then not affect my pipelines with the change in tiller Helm versions. Now I export environment variable. What I do here is basically I extract the chart version from my Helm chart itself, and then I basically write it to the CF volume. So every Codefresh pipeline step gets a volume attached to it, and you can write anything to that volume, and that volume is available if you export globally to the rest of your pipeline, and locally if you don't export it globally. So then I'm doing something called generating an OSS BOM and test coverage report. I'll show you what this looks like. What this basically does is runs some test reports as well as some free and open source license stuff through my Gradle file. And then it uploads those reports in HTML format to an S3 bucket, let's say. Then it builds the Docker image, tests the Docker image, and it pushes the Docker image to this registry over here. This is my private registry. Then it builds the Helm chart with the image that it created here in Docker build step. Then it tests the chart, and then it pushes the chart to my cluster. So this is the actual continuous deployment step. Here it has basically taken the kube context namespace and the chart reference, which I injected at environment variables at the previous step. Now let's go look at the interface. So this was the approve step in here, which basically if you want manual intervention, you don't want something to, let's say, go to prod automatically, then you would basically introduce a manual approval step. You can even integrate it with Slack, and it sends a notification to a particular Slack channel that, hey, somebody is trying to get an approval, and you can set up teams with specific members in them, and only when those members approve will the deployment pipeline proceed further. So that gives you a certain amount of access control as well in the Codefresh platform. So it's deleting the pipelines. Let's go look at the pipelines themselves. So you see all the pipelines have been destroyed because I ran that script from destroyer. I'm going to run the creator script now. This will go ahead and create all of those pipelines corresponding to different environments for me. So as a DevOps personnel, it gives you a lot of flexibility with the scripting in there. You don't necessarily have to come to the UI of Codefresh. It's fun. I would tell you that it's fun to come and do stuff at the UI. However, in the interest of time, if you wanted to script your deployment pipelines and then just check it into the GitHub repository, and then the developer is all set to go, that works as well. You will see the pipelines appear shortly. All right, here are the pipelines. So there's one for prod, for feature, for dev, and for canary. So that script automatically created my pipelines. Now let's do a little, let's see if my git trigger works. So I'm gonna just introduce some spaces and say, git commit testing pipeline dev. And then I'm going to push. All right, I pushed. Let's go see if the trigger works. I go to builds. Here is my commit message, and this is the pipeline. It automatically triggered the pipeline. So when a developer makes a change, They just commit the code and the pipeline automatically starts. All right, so it's gonna, I already walked you through what it does in the pipeline itself. It determines the tiller version after cloning the project so that it can run that particular version for subsequent steps. Then it exports the chart version and exporting environment variables. Then it generates the FOSS and test coverage report, builds, tests, and pushes Docker images, build, tests, and pushes charts, and then it finally deploys to the particular environment. Now, I would like to show you how you can very easily integrate with other tools in the ecosystem when you're using Codefresh. So this step here, this generate OSS bomb and generate test coverage report, have basically created these reports and uploaded to my S3 bucket, and I have access to them through my Codefresh dashboard. So you can see it provides the test coverage for this project. This is the free and open source bill of material that it has automatically generated for my project. And this is the test coverage report, and you have multiple views of it. In here, it's all the test cases passed. There were 144 test cases, all of them passed. You can see the timeline, you can see the behaviors and package, etc. All right, so that's about it. I think I am done. Thank you for listening. I hope you were able to take away something useful from this presentation, and please go ahead and ask any questions if you have. Dan and I will try to answer it.
Fantastic. Thank you very much, Apurva, for sharing what you guys have been doing. It's really cool to see a whole organizational kind of shift like this that's happened over the last year. You guys have done just an amazing amount of work. So we got a couple of questions, and so I just want to jump into those. The first one is from Roger. He says, this is great. When appropriate, can you zero in on why or how Kubernetes helps enterprises move to the cloud? Could they not do that before with a monolithic infrastructure? And I have some thoughts on this, but I'd love to hear your thoughts, Apurva, before we end me.
Could you please repeat the question? You kind of broke off in the middle.
Oh, sorry. The question was, can you zero in on why or how Kubernetes helps enterprises move to the cloud? Why can't they do that with just a monolithic infrastructure?
So you can move to Kubernetes with a monolithic infrastructure. However, you will not be able to, I mean, the first question is that, is your application cloud ready? A lot of times these monolithic applications, they are not cloud ready, and they were not built to scale in the cloud. So you don't have to necessarily use Kubernetes if you want to move to the cloud. You can even do a lift and shift, and it works the other way around too. You can do Kubernetes on-prem as well. So I don't think you should think of Kubernetes as a tool that allows you to move to cloud. These are two different concepts. If you are looking to maybe make your application hyperscale, like maybe even planet scale, Kubernetes allows you to do that. If you wanna reduce the burden on your cluster team or the team that does DevOps in your organization, then a lot of stuff that people do manually in organizations as part of system administration are already taken care of by Kubernetes. So I think you should decide based on these other factors as opposed to whether Kubernetes can allow me to move to cloud. Does that answer your question?
Yeah, I would add to that a little bit, Apurva. I think that what you demonstrated in your setup that I think does help with migration is the idea that you can actually just configure all of your infrastructure using the Kubernetes API and using just those YAMLs, which makes it a lot easier. So like if you had to move to the cloud and you had to learn, let's say AWS, or you needed to learn Google Cloud, or you needed to learn Azure, if you needed to learn all these different kind of what are essentially sort of proprietary APIs, versus the Kubernetes API, where you basically get this sort of universal interface that you can use both on-prem, you can use it in the cloud, and you separate that out and make it simpler. And I think that when you go and ask people why they move to Kubernetes, people talk about the scalability, people talk about the reliability, but actually the number one reason that people cite is increasing developer velocity. So, well, why does Kubernetes do that? How does it do that? Well, if you have a way to describe essentially what is your application infrastructure as code, that makes your CI/CD processes way easier. That makes it easier for people to self-serve and deploy their applications. And suddenly, just like you demonstrated, Apurva, you can stand up your whole infrastructure and move it very easily. That's a much easier kind of setup to have. And a lot of these people, when you're moving from like on-prem, you've been sitting in a monolithic world for a long time. You're used to all these processes being very manual, but you can basically automate all of this stuff when you're using Kubernetes. Now there are some tools for automating things outside of Kubernetes, but it's definitely much easier. But it does require you to containerize your applications. In most cases, that's actually not super painful. That's actually fairly straightforward. But in some cases, it's a little bit tougher. And to take full advantage of containers, you do want to start splitting up into microservices, assuming that your application is a large monolith. A small monolith is probably fine, right? But yeah, that's a great question. Cool. So
to add to what Dan said,
yeah,
I think we're out of time, are we? Okay, never mind.
I think we can do one last question. What is your approach in choosing Codefresh over other CD tools on the market?
So actually, one of my teams did evaluate Codefresh versus other tools. Codefresh wins outrightly because of its integration with Kubernetes. It has very quick and easy integration with your Kubernetes infrastructure. And I think it was built for container native deployment workloads. So it works really well. So technically, you could use Jenkins for your deployments, or you could even use Azure DevOps. However, the amount of scripting you would have to do with Azure DevOps is a lot more compared to what you would have to do with Codefresh. So it was, again, I have a relatively smaller team and resource constraint. I wanted the fastest and cleanest way to do this, and Codefresh was the winner there.
Thanks, Apurva, for that wonderful endorsement. I would add that a lot of people come to Codefresh from the CD side, because we also do have the Canary release built in, the Blue-Green release built in, and we didn't get super into the dashboards, but the dashboards where you can see all of your Kubernetes clusters, what's deployed, and then it automatically traces back into your CI and your commits, so you get a level of visibility that just isn't around on other platforms. Well, with that, I think we are out of time. If you have additional questions, feel free to put them in, and we'll try to email you answers afterwards. But big thanks, Apurva. Really appreciate you taking the time and showing us how Bosch has really embraced this cloud-native CI/CD world. It's very cool. And I believe you're going to be around at KubeCon next week a little bit, but certainly on Monday, there is a cloud-native CI/CD co-sponsored CNCF event. So anyone who's interested in that, you can find the details at what's the best place to go? I guess the CNCF website. I'll post it in the chat here as we close. Any final words?
Thank you, Dan, for giving me this opportunity to share my knowledge with the rest of the world. And I will see you at KubeCon.
All right, sounds great. We'll see you there, and I'll post the link to that event in the chat here. Thanks, everyone.
Perfect.